Okay, the clock is now 2 minutes past 3 here in Denmark, and I would like to say welcome to you all. I am Frank Lorentzen, and I'm the CEO of Danish AM Hub, the national focal point for additive manufacturing. We do everything we can here from our headquarters in Valby in Copenhagen to use this fantastic technology to rethink how we design, develop, and produce products. Not only because it makes perfect business sense from a technological point of view, but also because we fundamentally need to change how manufacturing is done. We need to move manufacturing to a much more sustainable direction and way of process. So today you'll meet two really great both speakers and also friends of our Danish hub, Handel and John Wilczynski. I'll give the word to John first, but I'd just like to put a bit of words to who we are on this session and on this call before we deep dive into the settings. First, the last year has been crazy. It has been intense, and it has been rough out there for manufacturing companies. But actually, if we look at kind of the AM international ecosystem as a whole, it actually looks quite good. I think because people are starting to get that there are really some benefits from this technology that we can harvest. Not only in terms of the technological side of things, but also in terms of bringing a bit of the value chain back in our own control, and also being more resilient to whatever may come in the future, because Corona might not be the first and the last pandemic or crisis that we see. John will talk about. John is the executive director of our sister organization in the States, America Makes, and he will tell us a little bit about how they managed to create both a process and also really a digital platform really that could scale 3D printed parts and designs and push them out to the front of the health system, of the healthcare system. So really looking forward to that, and thank you, John, for joining us today and spending a bit of time with us today. Also, in a bit of a half an hour, we'll hear from Sherry Handel. She is the executive director of Additive Manufacturing Green Trade Association. That's a long name. There's a bit of a piano playing. I really like it, but I think we'll get back to that when we're done here. Sherry is fighting kind of the same fight that I'm doing out there in finding and talking about the environmental benefits of this technology, understanding that AM is not a silver bullet that we can load inside our production and then everything is just green. There are advantages and there are challenges, and Sherry will put a bit of words to that. So also, Sherry, thank you very much for joining us today and spending a bit of time with us. Now, one of the purposes for today, and one of my and the team's main purposes, is that we need to learn from each other, really.
You just got muted, Frank. I can't hear you.
Here we go. They are really in a mature state when it comes to additive manufacturing in the United States, and we can just harness each other's experiences. That's the great thing if we're good at talking together and we're good at sharing these experiences. Also, John, Sherry, and I, we also will meet and engage in talks on what can we do together after this meeting. So if anyone has ideas, if anyone has questions on what you hear, fire them away in the chat, and I will do my best to gather them and to structure quite of a kind of a Q&A session after each presentation. So I think I won't spend a lot more time. I will just invite John to turn on his camera. Hello, here we go, John. And also, please introduce yourself and share your screen, and I will disappear. Take it away.
Thank you, sir. Pulling my screen up now. I think. Oop. How do I keep doing this incorrectly? 1 second, sorry about that. You'd think as often as we do this these days, this would not be so difficult for me.
Exactly.
It should be coming up.
It's all challenge. I think we have it here, John. Yeah, that's perfect. I'm off.
Okay. Sorry, it seems to be a bit delayed on my end. So, well, thanks to the our friends in Denmark. You know, I think we're all working in this very same space. You know, between ourselves and Sherry and you know, really across the globe, we've been trying to, for years, understand how to better utilize additive manufacturing. And what we're going to talk a little bit about today is, you know, what we've seen over here in the States. It's very similar to the story that we've seen really across the globe. First, I want to introduce you a little bit to who we are at America Makes. So America Makes is really, you know, a public-private partnership where we're trying to bring together academia, government, industry, to focus on developing additive manufacturing technology, developing the associated workforce. So how do we build human capital such that we're able to take advantage of this great technology that we're all working on? And then how do we build and make sure there is a ecosystem or a supply chain that is able to take the work that we're doing in the applied research community and actually transition that over into, you know, manufacturing and really into a viable, you know, career for folks and ultimately a business opportunity and you know, an industry. So we were founded back in 2012, and there's now a series of different innovation institutes here in the United States. The first was focused on additive manufacturing, and ultimately, you know, we've been working hard for the last 8 years to develop technology, develop this ecosystem, and develop the associated workforce. But what we saw almost a year ago to the day was, I'm on the East Coast of the United States, and you know, we were seeing, you know, we were delayed a few weeks from what you were seeing in Europe, and right in the beginning of March, we started to see everything, you know, become crippled because of not having available supplies, and really we saw the supply chain become immediately crippled. And that I remember this like it was yesterday, but you know, we started out having conversations, you know, as us folks trying to convene and coordinate a technology. We're really focused on making sure we're bringing information to the community and sharing information. And in a time when we weren't sure what was going to happen, most of our conversations were about, you know, where can we help support these folks who we know are going to be working remotely, and we knew our worlds were going to change, but we didn't know what that really meant at the time. That very rapidly transitioned into, you know, medical professionals and the system didn't have the products that they needed, and we saw the additive manufacturing community want to get involved and start asking questions. And as someone who, you know, is a membership driven organization, we have a couple hundred members that range from very small organizations to very large organizations. We saw everyone from makers to manufacturers getting engaged or trying to get engaged and asking questions. And that led us to basically reach out and start to utilize some of the relationships that we had to work with our partners across government, academia, industry, and beyond. And what we did was start to utilize and reach out to these connections. It ultimately led to where it really got started for us was in early March, right around this time last year. I had been talking to many people, and it was everyone from people calling me up wanting to know, should they buy all of the copper infused filament that they can find because they heard on a story somewhere that it was going to be an answer, and no one really knew what to do next. And then I had very large organizations calling me concerned around IP and rights, data rights to information, that they were starting to see models shared, and nobody really knew what to do. So that all happened March, and then we were working with a number of folks trying to coordinate a response. We were all wanting to help, but nobody necessarily knew what to do next, and that's all anyone was trying to do at that time. That led to us, through some relationships that we had, I actually crafted and submitted a letter to our Food and Drug Administration commissioner and called out 4 concerns that we as a additive manufacturing community had around, availability of information around part shortages. What was the real demand? What should we be working on? How do we know which designs to use? What was the direction from the FDA around, designs, materials, IP, and then finally, how are we going to get this product, once we do make it, out to people who need it? That ultimately led to something that has been a fantastic relationship here, where our Food and Drug Administration, our Veterans Affairs, or Veteran Health Affairs Administration, and the National Institute of Health all came together. We sat in this, what is, we've internally called the COVID 3D Trust, and it created a interagency arrangement across all of these federal agencies, where we saw folks coming together and really working on this program as a cross-agency team. It led to MOUs and a whole series of other things that has since been. We've seen other agencies get involved, other departments within our federal government, and it's ultimately led to a very immediate reaction where we were able to produce many components. Many of those stories have been told. And then what I'm going to talk to you about for the balance of my time is some of the work that we're working on today to try to assure that we are better prepared for the future. So how do we build something that is publicly accessible? One thing that has proven to be very needed early on and through the early phases of the response was people were looking for trusted information. And ultimately, having our federal agencies come together and using us as a public-private partnership, who were able to reach across industry and academia and even into the small maker community to get the right information to them, because nobody knew what to do. Most folks were not from the medical manufacturing community. So, this is a graph to demonstrate, what we saw happening in the early months. There was a rapid response. We worked really hard on bringing people together, much like we saw all over the globe. Many people wanted to help, but we needed to make sure we were working on the right thing. What we're focused on moving forward is really about scaling capability and then exercising that capability. So we've been, from the earliest months, been challenging what is it that we as a country and really as a globe need to have in place so that people can get access to the information that they need when they need it in a distributed manner. One thing I think we're all very proud of is how additive manufacturing has really demonstrated the distributed manufacturing model. We've talked about it for years, that this is, additive is an enabler to that working. We have seen it happened time and time again over the past year, where it has stepped up, and that's ranged from early on from face shields and different adapters to components for other medical devices to, a variety of other different implementations. We're now challenging, the community at large, I would say, and our own governments, of what do we need to have in place so that we're better prepared for the future. The only thing we are certain of is there will be more crises. Whatever they might be, there will be more. And we need to make sure that we have systems in place so that we're able to respond much more effectively than we were able to in this most recent and current pandemic. So what that's led to for us is the development of this program called AMCPR, or the Advanced Manufacturing Crisis Production Response. And what it is really about is, how do we bring together the community, the ecosystem, those that are, able to be involved and make a difference and support either the manufacturing community, the needs community, or the design community. And then how do we make sure we have that information available? Distributed manufacturing only works if people can get access to the information that they need. So that's led to really a two-pronged approach to what we're doing. One is engaging with the ecosystem and really trying to build out that supply chain. And then on the other side of it is ensure that we have a system or a tool in place that is able to actually support support this in time of need moving forward. The way we've done that and the exchange that we've built, and I won't get too far into this, but there's a variety of different ways that you can engage. At any point in time, we need different types of organizations, different types of people to be involved to help support a response, whether that's a natural disaster, whether it's a healthcare or a health emergency or pandemic, or there is just an issue with the supply chain. Those happen repeatedly. Some of what we're seeing happen, within the chip space today, and we've all, I think, no matter where you live or where you're dialing in from right now, every country has realized dependency on others, although it is absolutely needed, and that's a lot more macroeconomics come to play there. At a fundamental level, we all want to be able to take care of ourselves. So we need to understand, what do we need to have in place in order to do that. So we've built out this system, and you can read it here. And this is all going to be made available after the fact. But there's folks who need to raise their hand and say, I need help. I don't have this item that I need, whatever that might be. There is, sometimes we'll know what those are. So we have something here called the National Strategic Stockpile. And what we're trying to do is, how do we build out what is the digital stockpile that is available so people can go in and query that and get access to the information that we need. Sometimes we know, or sometimes there will be situations like during the pandemic when we didn't know we were going to need something. So there's a great opportunity for the design community to get involved. We need to be able to very quickly and rapidly innovate and ideate on concepts that we can then get to the manufacturing community so that they're able to supply goods that are needed. And then ultimately, we haven't talked too much about this. I mentioned it in the form, or using the term trust, but ultimately, one major reason that we got involved or started to engage in conversations was to make sure that the components that were being manufactured were meeting the needs of the healthcare community. Oftentimes we say this in our space of additive manufacturing: just because you can make it doesn't mean you should. We need to be able to communicate to that manufacturing community, whether a maker or considerations are, and everything down to how to label and package. Those were some what seem to be pretty basic needs that people who don't work in that space didn't understand. Another major area where we saw an opportunity was around education, and really it was more framed as workforce development. So I had multiple organizations call me and want to know how to get their workforces re-skilled so that they saw additive as a potential solution or as a potential bridge or opportunity to pivot because their current model wasn't needed. Something happened, whatever supply chain they might be a part of, where they saw a significantly, in some case, diminished demand. That left them wondering, what do I do with my people? And then at the same time, they saw this opportunity where additive was able to make components that were in critical need, but they didn't know how to get their folks trained. That ultimately led to a program. We're currently still working this. It's really a continuum or a pathway where folks can get engaged and get re-skilled and upskilled in additive manufacturing and associated technologies. And through that, we've built out a series of different opportunities to get engaged, from just simple awareness to make sure people understood what the technology is, why they should be involved with it, then kind of moving across the continuum where we started to create micro learning badges and then micro credentials that all ultimately then rolled up into industry recognized credentials, so that we were able to get information out to the community so that they were able to really leverage and get involved in the response. And that this is an ongoing opportunity. So nothing that we've done, whether in the States or across the globe, is something that, is going to go away. Although hopefully, as we make improvements and see the current pandemic hopefully diminish over the coming months, we'll as that happens, we still need a resilient supply chain. We know there is going to be opportunities and needs and issues with supply chain. So what do we do? How do we make sure that we're in a good position, whether it's in the States, Denmark, or anywhere else? We have, through this AMCPR program that we're working today, we've created a series of scenarios. So we showed it on that the diagram where there was a curve, the need to scale and then the need really to test. So what we're doing right now is testing the system. We've created a series of different scenarios. We're testing everything from a natural disaster related. So if there was an earthquake and we saw the inability to get water, clean water where it was needed, how does additive manufacturing community have the potential to make a difference there? If there is, we're, as you can imagine, doing some scenarios focused on the current healthcare crisis that we're in. We have, some that are focused on national security, where if there is a problem with a system that is down and needed, how do we get the right group of manufacturers involved in that? And that, is a pretty comprehensive system where we're looking at everything from different types of complexity, from process to product, regulatory considerations. Who are the folks within the manufacturing community that can respond? Do they even know there's an opportunity to respond there? Are they connected? So if you think of a natural disaster, if we don't have the ability to get them information, can we operate in low bandwidth environments, and can we get information offline to them so that they're able to respond? So we're going through the process right now of evaluating all of this. We will, over the coming 3 or so months, be demonstrating these scenarios. We're doing live demonstrations right now where we're going to have a requester put in and say, I need X number of units. It gets distributed out to the community, much like you could imagine needing as a regional response. And then we're going to have the manufacturer sent in, test, evaluated, et cetera, to see, to learn from this process. And, all of that is to help prepare us so that we can put forward a series of recommendations. So we're developing right now a roadmap for both the system as well as this concept. And the final product that will come out this summer is going to be an impact report, which will, one, capture what was done, why it mattered, and then also at the same time kind of look forward to say, this is what we need to be thinking about next. So, ultimately what it means to all of us is we know there'll be crises. We know we need resilient supply chains in both times of normalcy and times of crises. We can learn a lot from both of these scenarios, and we need to put systems in place, and then we need to test them so that we're able to take advantage of them when we actually need them. So with that, I will hand it back over to Frank to see if we have any questions to handle. Thank you for the opportunity.
Thank you very much, John. I know that a lot of the participants in this meeting are from our EU project Eureka, where we are creating a network for fast pandemic reaction. So I hope that everyone has taken notes, because I think that the thinking you present here is really cool, and it shows that you have really tried to do something new here. But it was also kind of a new problem. So
yeah, no, I actually, we do one thing where we're trying to keep a pulse on what's going on all around, and I just had a article about considerations when, I'll say, resetting a factory that was, I believe, produced by that team. Just hit our radar this week. So yeah, I think we're very interested in the same kinds of things.
Yeah, good to hear, John. I have one question from my colleague Aya, which is, if you look back at all of the crazy events. I've never been so busy as I were in kind of the first Corona wave, because suddenly people thought that we could 3D print tons of things, right?
Yes.
But if you look back, is there anything you would do in another way, or you would wish you had done more of, or is there anything you think this is really a key learning point for me?
Yeah, I think for us, the biggest problem here, and I believe it was everywhere, was understanding of demand and priority. So we knew things were really bad, but we didn't really have a good sense of how bad they were and where exactly they were bad and what we should be doing next. So in a way that led us to have a lot of people. It was brute force, where we had folks in many cases in hundreds of parallel efforts working against a problem set. Wow, there was another problem alongside of that wasn't identified, or wasn't, it wasn't at the top of the list at the time. It led to a lot of, so right now, one of the most powerful things I think we did was the relationship with FDA, the VA, and NIH here. And I knew those folks from a variety of past activities. In particular, the NIH 3D Print Exchange is something that existed for a very different reason. I just had this call yesterday with Megan McCarthy, who runs that, and said, I just looked at your text from a year ago when you sent me and said, hey, I need to talk. Can we use this system? But what we saw, there's now 600, 700 different designs on there that have been, at some level reviewed. You can only handle so many of those. There's just not enough resources to do that. We have 200 different face mask designs. You don't need that many. It's great that many people wanted to get engaged, but again, to me, it goes back to demand and prioritization. And that's one thing that we're trying to capture right now as we're writing up this impact report. Is we all learned a lot from this. We were able to show, we have numbers in the tens of millions of product that had been produced by additive manufacturing.
That's fantastic.
And I'm sure that's, that number is needs to be multiplied by many when you look across the globe. But we still don't have a great sense of what's needed when. There's not a centralized, for us here at least, there's not a clean centralized demand. So I don't know that I can do anything different right now, but we know we want to, recommendations coming forward are we need to have a better understanding of that. Because if I need to go disperse the the design community to go work something while having the manufacturing community go solve this problem, or start doing bridge production with AM and the conventional folks, starting to retool, we could we collectively, we were in no way single-handedly did any of this. This was thousands of people working really hard to do it. I think another very powerful thing for us, in talking even to some of our federal partners, was the role of a public-private partner in a response. It's easy for me to talk to industry and academia and also work with government. It's difficult, especially while everything is, on fire and nobody knows what's going to happen next. The federal government can't come out and say, go do this next, and we obviously have to watch what we say, but it is easier to have somebody, be part of all of those conversations than it is to have to wait. Granted, another very large part of what we did, we came up with something called regulatory considerations, where we put out where people could look at it and say, if I need to manufacture nasal swabs, it was everyone's favorite story for a while. If you want to do this, you have to have all of these systems in place. You have to register and list. You need to be this kind of, that was not something people understood. So I think that was a very important role. Although it is all documented and available, it's not something people can understand. So a manufacturer normally makes automotive widgets, doesn't know how to engage with that type of site. So that's a long answer too, and I don't know if I have a good one, but
no, I think that I think that one of my key learning points from your experiences is the stellar cooperation between public and private, really. And there's a couple of questions here from both Trond and Jens that has to do with visors. And I think that at the beginning of the Corona crisis, where everyone was like, "Oh my God, we're hit in the face," everyone could see that the most obvious thing to do is just to print visors, because there was a terrible need in the front line for PPE equipment. And I think in Denmark, and maybe also in the Nordics in general, we had a bit of challenges with that, because our authorities didn't have a process for how do we make sure that those visors are the quality that we need them. And what happened, instead of professional manufacturers printing visors, you would have 3 or 4 weeks where private initiatives would just arise in Facebook groups and other places, and then just ship the visors. Mm-hmm. So that is really one of my key learning point here, also from your fantastic example, is that we need to create some kind of system where, if people are in desperate need, and I had doctors calling me that they were on their way to buy, swim glasses, mm-hmm. or something else. Or maybe not swim glasses, wouldn't help that much. But they were on their way to buy all crazy stuff, because they just were in desperate need. And then we just had kind of the old regime in terms of how to approve, how we do that, and 3D printed parts just doesn't work that way. Mm-hmm. So that deep cooperation between the authority side and the approval side and the design side, it is a massive work to get that running. And it's really impressive what you've done here, John, and your organization. So I just wanted to end there. Thank you very much, John. I know we could talk about this, for for ages, and we have done so already, but John's slides will be shared afterwards. Also, if there are specific questions that we didn't have time to cover, do write us or me directly an email, and I will put you through to John. So thank you very much, John.
Yep, thank you.
Now, luckily, Corona is only a short-term thing. Let's all hope that we can be done with that till summertime, and everything is good again. And then we have a much worse problem that Sherry is here to tackle with us, and that's climate change. It has been really difficult for me the last 1.5 years to find really good facts, documents, reports on how to use this technology in a sustainable manufacturing process. So I'm so glad that Sherry is here today. We are a member of AMGTA, and we support the fantastic work they're doing. So I won't speak, I've already said too much, so I would just hand you the screen. Sherry, feel free to share, and I will disappear again.
Thank you so much, Frank, and it's a pleasure to be here today with you, your audience, and of course, John as well. I appreciate the opportunity to speak on this topic. And at this point, I'm going to now share my slides. And you should hopefully be able to see everything. Good, excellent, appreciate that. Okay, it's coming up for me too. So as I mentioned, I am Sherry Handel, Executive Director of the Additive Manufacturing Green Trade Association, also known as the AMGTA. And the AMGTA was launched at Formnext in 2019. I came on board as the trade group's first executive director last February. And the AMGTA is a global nonprofit organization that meets certain that is open to any additive manufacturer or industry stakeholder that meets certain criteria to sustainability of production or process. And my role is to build and grow this new trade group globally and to work with our members to advance sustainability in additive manufacturing. And it's so exciting to see sustainability in AM gaining momentum as more and more companies strive to reduce their carbon emissions and other environmental impacts. Existing research on sustainability in AM tends to either focus on waste, energy use, or machine emissions to manufacture a part. I apologize here. The slides just went all the way to the end. I'm sorry about that. We'll go back to here. Hopefully this will come through okay. I apologize. My slides, I see it on my screen, but it's not matching up. I gotta bounce back. Sorry about this, everybody. Not sure how else to do it. Okay, as you see, we are now back to where we started. Okay, there, perfect. Okay, so the challenge is that there is limited academic research that focuses on life cycle assessment in AM. And to help the AM industry advance environmental sustainability, we need solid and reliable sustainability data and metrics. And at the AMGTA, we are driven to provide the industry with this much needed research. And as I mentioned, there's limited published research that really focuses on the life cycle assessment, which is a comparative study of an environmental impact a part or a product has throughout the stages of its life, from cradle to grave. And as you see here, we have several steps in the LCA process. The AMGTA is addressing this lack of real research by commissioning studies that include life cycle assessments, or LCAs as they're commonly known. And LCAs analyze the part at each phase of its life, from resource extraction, material processing, part manufacturing, assembly, distribution, use, up and through the part's eventual end of life when it is no longer useful. We want to fully understand what the environmental impacts are all along the way. The AMGTA recently published an AM metal sustainability literature review paper titled State of Knowledge on the Environmental Impacts of Metal Additive Manufacturing. We realize, of course, that there is a strong need as well to focus on polymers and other materials, but we had to start somewhere. And our board of directors determined this was the best course of action for us based on our membership interest at that time. This paper was written by researchers from Delft University of Technology and Dartmouth College. The report is available for free on the AMGTA website in our resources section. As part of our first published report as an organization, the AMGTA commissioned Dr. Faludi from Delft University of Technology to put together a systematic review of the current condition of literature regarding the sustainability of metal additive manufacturing. And what we found was, unsurprisingly, there is not enough good research out there to fully capture all aspects of additive manufacturing as it relates to sustainability, especially not enough research to compare the impact of an additively designed part, one that has been optimized through the virtues of AM, with a similar component manufactured using traditional methods. This presentation is going to highlight the scarcity of research and motivates us as an organization to start developing good research that examines these improvements. Part design and end-use utility notwithstanding, Dr. Faludi was able to pull together basic facts regarding AM as a manufacturing process versus conventional manufacturing. In this presentation, we will go through most of the life cycle stages of a part, from raw material extraction to manufacturing, use, and end of life. The only thing we'll skip is transportation because the environmental impacts of transporting parts, whether they're 3D printed or conventionally produced, is usually insignificant, a rounding error compared to the impacts of other life cycle stages. Finally, at the end, I'll leave you with next steps, both to improve our knowledge on how to make AM more sustainable and to apply the lessons we already know to green the industry. First in the life cycle of any part is the mining the ore and processing it into pure metal. The process includes shaping it into a form that's useful for manufacturing like ingots, or in the case of AM, ultrafine powder. As you can see from the graph, different materials have very different embodied impacts. Aluminum has about double the carbon footprint of stainless steel, while titanium is over 7 times. Processing these refined materials into powder doesn't add that much impact. Please note that these are virgin metals. Recycled aluminum actually has 95% less embodied impacts per kilogram, so it's even better than recycled steel. This is definitely an area for future study. A material's impacts don't end with initial processing. They also influence manufacturing impacts. The higher the metal's melting point, the more energy you'll need to fuse it during printing, and higher thermal conductivity means the heat you apply to fuse it will be dissipated more, thus reducing efficiency. For laser-based processes, the reflectivity also matters. More reflection means less of the laser's energy heats the material to fuse it. This makes aluminum processing energy higher impact than you might expect. There's a whole world of data on the environmental impacts of traditional manufacturing. Most of it quantifies the impacts per kilogram of material processed. You can find carbon footprint data, but also lots of other metrics from acidification and ozone layer depletion to water use and land use. Good life cycle assessments measure up to 18 environmental impact categories, but here we're just looking at carbon footprints, because LCAs of 3D printing have been quite limited and most of them only do measure the CO2. We can look up the carbon footprint per kilogram of any conventional manufacturing process in lots of databases. We used one of the best, Granta's CES EduPack, but it has no data on AM because there aren't enough LCAs out there. So to compare the impacts of AM to conventional manufacturing, we had to compare LCAs of AM published in academic journal articles to the Granta database. If you compare the processing energy impacts of AM to casting, extrusion, rolling, forging, or wire drawing, anything except machining, you'll see that AM has between 5 to 100 times the impact per kilogram. But 5 times is very different than 100 times. Why such a wide range? Partly because conventional manufacturing methods can have very different impacts from each other, and partly because very few studies have been done on metals AM carbon footprint, much less directly comparing it to other manufacturing methods, so we don't know how repeatable these numbers are. More studies need to be done. But you might be reassured to hear that if you measure not just processing energy impacts, but also the embodied impacts of the materials themselves, we saw in the previous slide, the ratios go way down. Now 3D printing steel is only 4 to 8 times the impact per kilogram of the other processes, and titanium is only 1.4 to 1.7 times. Fear not, however, it is important to note that these numbers are all design agnostic, meaning that operational improvements in design, such as weight savings or a combination of traditional manufacturing steps, are excluded. For example, look at these cubes. Does anyone think that additive manufacturing would be the most sustainable way to manufacture a basic cube like this? Of course not. As we will discuss, the true power of AM is in the design and final part geometry, aspects that a basic fabrication comparison such as this ignores. This is a crucial distinction that we will study at length through the use of life cycle assessments, where intricately designed and optimized components manufactured additively will be compared to their traditionally manufactured counterparts. Now, hopefully you're wondering why in the last slide I didn't include machining. Well, here I'll explain why. The reason is because machining impacts are different than all other types of manufacturing methods, because you actually start with a cube or a block of metal and you cut away some of it. The impacts increase per kilogram of material you remove, not per kilogram of material you add. This means that comparing environmental impacts per kilogram of material is a fundamentally bad metric. In the LCA world, it's called a bad functional unit. A better functional unit would be a specific part you manufacture both by machining and by 3D printing. That provides a fair comparison for the actual end goal, whatever the function the part has. There are very few studies out there that do this, but here is one by Prioroni and others directly comparing EBM of titanium to machining it. And they compare them not just for one reference part, but for 3 reference parts. Part 1 on the bottom here, ID1, part 2, ID2, part 3, ID3. You see the CO2 emissions on the left. And machining is noted by the crossbars going diagonally to the right, and AM, EBM is noted by the crossbars on the second bar for each part. And they compare them not just for one reference part, but 3 variations on the reference part, from totally solid in the first case to partly hollow in the second case to very thin-walled hollow in the third case. The graph compares the impacts for all 3 parts. For the first part, totally solid, EBM of titanium is around 20% higher carbon footprint than machining. But for the partly hollowed part, it is slightly lower than machining. And for the totally thin-walled part, it's less than half the carbon footprint of machining. This is what was meant regarding the prior slide and why design is so important. So part geometry matters a lot, and we need LCAs that make fair comparisons like this. Interestingly, because this covered several scenarios, we can also see the crossover point where AM goes from being worse, and you can see that here in the crossing of these 2 diagonal lines, to becoming better than machining. That can help us make more precise decisions. As mentioned in the last slide, something this study does not do, but which we need more of, is to measure different utilization scenarios. For example, this part isn't very big. The printer might have been able to print a dozen or more of them at once. Since some of the processing energy isn't just the E-beam, but also the warm-up, cool-down, motors, etc., printing many parts at once this way is more efficient. But you might even get better numbers than this. But if the printer sits idle for a long time between prints, still using energy, that makes its carbon footprint much worse. We could also measure, or we should also measure, utilization scenarios like this in LCAs to get a clearer picture. Also notice that in this graph, the impacts of the EBM process were always bigger than the impacts of the machining process. But they don't need to be better if you make the whole system better, because the thin-walled part used so much less raw material than to 3D print versus the block and cut away most of it, versus to start the block, I should say, and to cut away most of it. And because titanium is a really high carbon footprint material, that made the whole system better despite the higher processing costs. And to illustrate how AM can sometimes be a greener technology than conventional manufacturing, even if it has a higher process per kilogram of material processed, higher impact per kilogram of material processed. That key point here is to find places where AM for design can be either one, first reduce the material embodied impacts. This is usually by reducing the part mass, but you could also do it by finding a lower impact material that is just as strong, but doesn't work actually in conventional manufacturing. Even if the lower impact material isn't as strong, you could compensate with clever geometry. Second, consolidate parts so that you can avoid a bunch of conventional manufacturing operations. This photo is of a GE engine that, when conventionally manufactured, required 855 parts, but their design for AM cut it down to just 12 parts. So even if the AM process energy is 10 times the conventional process, if you have to do only 2% of the number of process steps, you might end up saving 80% in processing energy. Now, GE didn't measure the energy impacts here, so we don't know the numbers, but it would be interesting if someone would find out. And the third thing you can do is design for AM such that you improve the part's performance during its use phase, or otherwise help the bigger picture beyond manufacturing. For example, lightweighting parts saves fuel in aircraft, or using metalloceramic alloys that enable more efficient engines, but can't be machined. Again, further research should test the limits of these improvements, both to see what's possible in the best case scenario and to avoid greenwashing by seeing where we might assume there are benefits, but in reality, there aren't any. To improve processing energy impacts, either as the operator of an existing printer or the designer of new kinds of printers, there are several things you can do. Here are some important ones. Utilization makes a very large difference. The same part printed on the same printer can have over 10 times, sometimes 20 times the environmental impact per part just from printer utilization. So work to enable the sharing of printers to fill the print bed, printing many parts at once, and to minimize idle time between prints. Idle time can be surprisingly important because some systems use almost as much electricity when they're just sitting there as they do when they're printing. First, choose materials that reduce processing energy. This is different than choosing materials with low embodied impacts, but you can do them both at the same time. This generally means metals with a low melting point, low reflectance, and low thermal conductivity. These can help by several percent. But if you want to make radical innovations, consider how you might eliminate the need to melt things entirely. That could radically reduce energy demand. Post-processing is not usually a big impact, but minimizing it can help minimize overall impacts. Finally, one of the benefits of AM versus conventional manufacturing is avoiding tooling for small numbers of parts produced. Luckily, the environmental impacts follow the same trend as the economics here. The crossover point where AM becomes lower cost than conventional manufacturing won't be exactly the same as the crossover points where environmental impacts become better, but you could calculate them the same way. So in the interest of time, I'm going to skip a few of these, but all of this is covered in great detail in the paper. I just want to focus on next steps for research, and then we'll take some questions. This leads us to next step. What does the world need for green metal 3D printing? First, we need a lot more research, as you've heard me mention many times, because I told you that there isn't really that much research out there on LCAs in 3D printing. More life cycle assessments can help us understand where the environmental benefits and problems of metal AM are. And of course, this is true for polymers and other materials. And to avoid greenwashing and find great opportunities, set our priorities to improve and help us benchmark current impacts so we can set the measurable goals of how much we think as an industry we can improve. And what should these LCAs do? First, we want to measure more printer technologies. Only a handful have been measured so far, and they haven't been well compared to each other, much less to conventional manufacturing. SLM and EBM are okay from the research, but DED and its variants have almost no studies measuring their impacts, much less making comparisons to conventional manufacturing. And second, more LCAs should consider all life cycle stages of printed parts to understand whether manufacturing impacts are even a priority for most metal AM parts. And lastly, LCA should have more fair comparisons, not comparing impacts per kilogram of material, but per part produced. These should have varying geometries relevant to their applications. And with that, I do have other remarks, but I do want to be respectful of the time here and go ahead and take questions.
Thank you, Sherry. And please, participants, if you have questions, fire them away in the chat, and I will try my best to gather them for a couple of questions. Not surprisingly, I really agree with you, Sherry, on your point in looking at the geometry, because I often find myself in kind of heated debate with researchers that would calculate, if I produce 1 ton of polymers with AM and I injection mold 1 ton of polymers, what is the comparison? And I would say I would never do that. I would, I have to use the design freedom inherited within AM to create, a whole new product. And then from that, I can even maybe make that even more energy efficient. And then you compare. So I think that's really a key point that we need to highlight and just need to really take into the future research also within this key area. And then another point I'd just like to hear your thoughts on that is on the energy side of things, which is also a critical issue in terms of the printer, right? Because if you print one part, obviously you would use more energy than if you just injection mold it really fast in a really efficient injection molder. And I'm thinking that is right. So I would just encourage everyone in the world to come to Denmark, where we have a lot of wind farms, where we have stellar energy security and supply, and also to invest and place your production and manufacturing systems here, because we would be able to almost produce in a CO2 neutral way if we do so. Or is that somehow untrue, Sherry? How do you feel about that on the energy consumption side of things?
Well, I think considering all the different, platforms around the world for the energy grids, they're very diverse. And some regions, like just here in the United States, there are certain states and certain parts of states that have a completely different energy grid matrix than others. So I think it really does depend. But I think the key points of this research really show the need for more research. It's just like, this is just the tip of the iceberg. We are just beginning this journey, which is what this organization was really established to do, is to help advance sustainability in AM. Well, how can we best do that? How can we best answer questions like the one that you posed? And we found that life cycle assessments really are a good measure to accurately, like we said, fairly compare AM to conventional manufacturing. The LCA is really the way to do that. And the point about the Prioni study was they actually used 3 different parts that had different configurations, and then you could really see the advantage of additive manufacturing when you looked at part 3. That's when things got really better in the comparison for AM versus traditional. But AM is not a silver bullet, like you said. There's going to be instances where it's clearly not the best choice, and then there's going to be others where nobody really knows because there's no research to back it up. So when we're talking to customers, you're talking to your end users and your actual customers that you contract with, if you're a manufacturer, and they want to be able to validate what you're saying, that AM truly is more sustainable, you need that research to back it up. Otherwise, it could be considered greenwashing because you really don't have proof. You have no evidence.
Yeah, thank you. We have a couple of questions here. I will do my best just to take, just to select one of them, mindful of being mindful of the time. How do we convince manufacturers and companies to think about reducing CO2 and not only think about reducing the cost and the time in production? Is there anything it's not a simple answer, it's not a simple thing, but is there anything you've seen that could help with that?
Yeah, I think from the customer demand side, we're seeing the manufacturers that I'm talking to that are approaching us that are hearing about the AMGTA. What they're saying is their customers are now mandating it. They're hearing from their customers that they want validation that AM and their processes are more sustainable. So more transparency in the supply chain is one of the key areas where there's more scrutiny. And I think this is a progression. This is really in its beginning stages. I think we're going to see a lot more of this. So those manufacturers that are addressing this sooner rather than later are going to be the ones that are going to most benefit from this new trend that we're seeing. So I don't know that there's anything you could actually say to them. I think it's when the customer says it that they pay attention.
Yeah, exactly. I think that's a good sentence to end this this hour with, Sherry. Thank you very much for your presentation. And as you said, we're only in the beginning of this long journey, and be sure that we will travel together with you. I noticed from your email signature that it says sustainability is a journey, not a destination. But let's try to get to that destination together. Thank you also, John, for being with us and sharing your fantastic experiences. And to all on this call, we will just wrap up some of your questions and get back to you all, and we will share the presentations from today. And do get in contact with us if there's anything we can do or we can work together on. And do have a great and fantastic afternoon and day in the States. Thank you, everyone.
Thank you.
Thanks all. Bye.
Thank you. Bye.
Thank you.